In this video, we're going to go over the paper called Gradient Harmonized Single Stage Detector. Let's go over the abstract first. So one of the key problems in single stage detectors is the disharmonies during training, namely the imbalance between the quantities of positive and negative examples as well as easy and hard examples. In this paper, first of all, they represent these two disharmonies in terms of gradient. And then they propose a novel gradient harmonizing mechanism, or GHM, to deal with these disharmonies. And this works for both cross-entropy-like losses and regression losses, such as the smooth L1. They propose two loss functions, GHMC and GHMR, C and R standing for cross-entropy-like or classification losses and regression. The idea is to balance the gradient flow for anchor classification and for bounding box refinement. And they show significant improvements. One of the key challenges in having a single stage detector is to deal with the imbalance between easy and hard examples, type 1, and positive and negative examples, given that the large number of negative examples can overwhelm the training. There have been mining-based methods such as OHEM, but they have their own limitations. Focal loss was also another method, which is not as straightforward as one would hope. So what's going on in this work? The first thing is to represent this class imbalance as gradient and in terms of gradient. So the key here is that they want to mention that the imbalance in difficulty, so the class imbalance can be represented as imbalance in difficulty, and that can be summarized to the imbalance in gradient norm distribution, meaning that a little magnitude of gradient norm is what you expect with easy examples that are well classified, and bigger norms for the misclassified ones. Looking at the distribution of the gradient norm can tell you something about whether or not the examples that you've been dealing with was easy or hard. They also claim that the imbalance of examples with different attributes, hard versus easy, positive versus negative, can also be implied by the distribution of the gradient norm. Looking at this figure, for a converged model, this figure represents the distribution of gradients, and you have the number of samples here. And looking at the distribution of the gradient norm in this log scale, you get the idea. You can see that there are a lot of samples with very small gradient norm, indicating that basically these are those easy examples that they claimed overwhelmed the training, which is discussed here too. They also figure out that the density of very hard examples is also slightly larger than the medium ones, which they refer to as outliers. The reason why is that the distribution was for a converged model and they still exist stably, even though the model was converged. Now, gradient harmonizing mechanism, which is the contribution of this article, focuses on the harmony of gradient contribution of different examples. Namely, it focuses on the statistics with respect to the gradient density and then attaches a harmonizing parameter to the gradient of each example according to the density. As you saw in figure 1, using the GHM, the easy examples and outlier examples are both downweighted. This means that, these two that might overwhelm or confuse the training mechanism are now play a very smaller role with respect to what they were doing before. Reformulating the loss function is something that, you can essentially consider as equivalent to modifying the gradient. They proposed GHMC, for instance, and this loss function is elegant because it doesn't have many hyperparameters to tune. GHMC is a dynamic loss, which depends on the changing gradient density in the mini-batches. And for even the box regression, they also propose a GHM-R, and they show better performance. So going over the contributions of this article, they first reveal the essential principle behind the significant example imbalance, and then they propose a novel gradient harmonizing mechanism. They embed the GHM philosophy into the loss for classification and regression as GHMC and GHMR, and they train a single stage detector without any data sampling strategy, and then they achieved the state-of-the-art results on Cocoa benchmark. Here is a summary over the related works. First, consider a candidate box. For a certain class, P is the probability that the model is predicted for it, and P star, which is a binary variable, is the ground truth. So this one is a probability, and this one is the ground truth. So if you write the cross-entropy loss between P and P star, if P star is 1, this is going to be your cross-entropy, and if P star is 0, this is going to be your cross-entropy. Now let's say X is basically the logit and P is sigmoid of X, meaning it is 1 minus X of minus X. This means that consider the case of P star being 1, you're going to have minus log of 1 minus X minus X. This becomes log of 1 minus X minus X. Now this is your cross-entropy loss. Now, if you consider the partial derivative of this cross-entropy loss with respect to X, you're going to have 1 divided by 1 minus X of minus X, because this is the derivative of the logarithm part, and you have minus 1 times X minus X, which becomes this. And this is P minus 1. Same way you can do the computation, and you will get that the partial derivative of cross-entropy loss with respect to X is P minus 1 if P star is 1, and otherwise meaning that P star is 0 is going to be P. And this can be simplified as P minus P star. Now they have defined G, which is P minus P star's absolute value, which if P star is 1 is going to be 1 minus P, and otherwise it's going to be P. And they consider this the norm of gradient with respect to X. You can see the distribution of this defined G in this figure, and you can see that even though the log scale has been used, the number of easy and very hard examples are actually very high, and this is something that this work is trying to deal with. For training examples, gradient density function of training is defined like this. Now let's see what this means. You have n examples. Gk is the gradient norm of the kth example, and delta epsilon of xy is 1 if x is larger than or equal to this and this. In other words, if x is a member of y minus half epsilon to y plus half epsilon. Otherwise, it'll be 0. And this is also defined as minimum of g plus epsilon 2 minus maximum of this. So basically you're truncating these values and then you sum them up. Now they define the gradient density harmonizing parameter beta as n divided by gd gi. Or it can be written as the inverse of gdgi divided by n. This indicates the number of examples with the gradients norm in the neighborhood of the example I. Consider a case in which basically g's are uniform, follow the uniform distribution. In that case, the gd of gi would become n, because all the g's are basically the same value, and then beta would become 1. In other words, no effect. Now let's go over the GHM-C loss. The gradient harmonizing mechanism C loss is defined like this. You have n examples, so as usual, you have to average over these. And for each example, you have to cross entropy loss between Pi and the ground truth. Now this time you also multiply it by this as well. If you think about this, consider the very easy examples. The number of examples with the gradient with the gradient norm in the same neighborhood would be very high. So this term would become high. This means that the corresponding beta would go down, and their impact on the overall training would be reduced. If you look at this loss here, you can bring in this 1 divided by n, and you can see that you have 1 to n. The cross entropy component, for example, I, divided by this. And this, as you remember, was the gradient density. Looking at figure 3, you can see that both focal loss and the gradient harmonizing mechanism sort of deal with the large number of small gradient norm examples that were basically the easy examples. However, the GHM loss also deals with the outliers as well. To be able to compute the gradient density for each one of the examples, you're going to have to do ON2 computation, which is extremely expensive. Even when parallel computing is involved, it still is not very feasible. And the best algorithm and the best order of complexity that one can expect is a sorting followed by a queue, which is going to be ON log n, which is still a lot. So they do some sort of a quantization called unit region. They divide the range of space of G into individual unit regions with a length of epsilon. So there's going to be 1 divided by epsilon equal to m unit regions, and Rj is going to be the unit region with index j. So this becomes this. And Rj with capital R denotes the number of examples that lie in that. So consider that the index corresponding to G is T. This means that G is in this span. Therefore, the index to the function to the units region that G lies in will help determining the approximate gradient density, which is computed like this. The number of examples that lie within that G times the total number of regions. But to better understand this, you can basically do R int equals GD hat G divided by M. This means that GD here is, again, the number of examples with the close gradient to the example G, to the example that produced this G. And this you expect to be equal to this divided by total number of regions. This approach helps reducing this complexity to OMN. They have also used the exponential moving average in order to deal with the noisiness of the statistics, because some of the extreme examples just basically exist in a couple of mini batch of statistics, and the noisiness can be dealt with using the exponential moving average. So they basically do that on the R values that denote the number of examples that lie in the jth unit, and then they use S, which is like the smoothened version of R, to compute the gradient density approximations. Now we get to the regression version of this loss. Again, when you have the parameterized offsets here, you have the ground truth as well, and then you use the smooth L1 loss with this basically format to compute the regression loss, which, having a delta, is defined like this. Now one can show that if you define D like this, the partial derivative of the smooth L1 loss based on Ti is going to be the same as that versus D, and then it can be shown that it's going to be like this. To follow this smooth L1 loss, they propose the authentic smooth L1 loss, which is like this, and shares the same properties as the smooth L1 loss, meaning that when the D is small, it's going to approximate a quadratic function, and when D is large, it's going to approximate a linear function. And looking at the derivative of ASL1 by D, it's going to be shown as this, having a range of 0 to 1. In practice, this value for mu is chosen. Therefore, the gradient norm of ASL1 is defined like this. Using the same approach as before, they define the GHM R this way to harmonize the gradients, this time for a regression problem. The difference when it comes to bugs prediction is that this time even the easy examples basically play an important role because the bugs accuracy and localization accuracy is more important. GHMR helps basically weighing down the outliers and also magnifying the importance of the critical easy examples. In this page and the next one, you're going to see some details on the experiments. One of the key important points is that they have used RetinaNet as the network architecture of their backbone, and they have an 800 pixel image scale. Batch size of 2 per 8 GPUs, meaning with the effective batch size of 16, and they have shown that they have achieved good results.